First sort of administrative thing I just wanted to mention is a lot of you have been facing this occasional and unpredictable issue with your debugger losing connectivity. And the inelegant solution up to now has been unplug and replug it, basically. So after lecture today, I have a whole bunch of new debuggers that are of an entirely different variety that I hope will solve this problem. So this afternoon, if you're working in on your webcams, you see me poking at your stuff for a couple minutes, that's what I'm doing. I am hoping that replacing all of the debuggers with these ones is going to resolve that issue. I think that it will. Any questions from anyone? Lab 1 going okay for people? People seem to be making pretty good progress. And I think today we'll fill in maybe just a couple remaining gaps for folks.
Just one comment about the programmers. When you pull down the properties tab for the project, the PixKit3 would no longer be there. Instead, it would be called MicroStick. You should see a device called MicroStick with a serial number next to it, and it may have to reconfigure the MicroStick, but that only happens once.
Yeah, thanks. So when you click that download program to pick button, it'll throw some warning and ask you to select a new debugger, and you'll see there'll be a green icon and a serial number next to the MicroStick. And if you mouse over, it'll say MicroStick. It might not say that just in the window, but if you mouse over it, MicroStick comes up. Okay, any other questions? In that case, I'm going to share my screen. I want to go over direct digital synthesis today, which some of you have been sort of experimenting with in lab and sort of getting a phenomenological understanding for, and hopefully today we can give a theoretical understanding for that too. I want to point out that if you go to the course website and scroll down to, many of you have already found this, but if you scroll down to the applications section, the first link in here is a direct digital synthesis webpage, which has all of the content that I'm going to go over today in a more sort of expository, verbose, sort of meant to be read format. So I'll point you to this if you want to review anything from today. And what I'm actually going to use in class today is just a modified version of that web page where the content has been sort of bullet listed. So it makes a little more sense to talk to it without having a bunch of paragraphs up here, and separate it out so that I can only have one thing on the screen at a time. Okay, so direct digital synthesis, as you all are aware by now, this is a strategy by which we can produce output sine waves through a DAC with an extreme amount of precision. So the accuracy with which you can produce a tone of a particular frequency using direct digital synthesis is pretty astounding if you set it up correctly. And we'll talk today about sort of the degrees of freedom in this algorithm and how different choices affect that accuracy. But with the correct setup, you can synthesize sounds with phenomenal accuracy. So I want to talk through this sort of from the beginning and just go through it to the end, because the consequence ends up being, the algorithm itself, as I've mentioned before, ends up being really, really simple in the sense that it takes very few lines of code. It ends up being about 2 lines of code that does all this. And if we step through it systematically, I'm hoping that those 2 lines of code are going to make a lot of sense. So I'll start with sort of the central observation upon which this algorithm is built. And it's sort of an abstract one, but if I play this animation, this might make some sense. So I'll start by just reminding folks what a sine wave is, because perhaps you haven't actually thought about that in a while. And what a sine wave is the projection of a rotating phasor, some rotating vector, onto the imaginary axis, the vertical axis. So in this diagram, you can see we have some phasor in red rotating, and the sine wave is the projection of that phasor onto the imaginary axis, right? So as this rotates, we're streaming out a sine wave here, which is the projection of that phasor onto this wave. The observation upon which direct digital synthesis is built is that this phasor completing one rotation is isomorphic, which is to say sort of it can be thought of as the overflow of some variable. So if you think about this, consider this angle that's being drawn here as this thing rotates. So this angle goes from 0 to 360 degrees or 0 to 2 pi radians. And the observation is that if we represent this angle with some 32-bit variable that we'll call the accumulator, and we scale this angle such that it is at value 2 to the 32 when it completes one rotation and at value 0 when it starts, which is basically the same as saying we're going to divide these 2 pi radians or these 360 degrees into 2 to the 32 steps. Then when this phasor completes one rotation, the variable that we use to represent that angle will overflow. So what I have here at the top of this diagram, I have two pieces of information at the top of this diagram. The first is the phase angle in radians, which you can see going from 0 and walking up to 2 pi radians. And then beneath that, I have a 32-bit variable. I have this in binary format so that you can see all the 32 bits. And this variable is counting up with the phase angle at a different rate, right? Because we have it scaled differently, but it's counting up with the phase angle. And when the phase angle overflows from 2 pi back to 0 radians, this overflows from 2 to the 32, which is all ones, back to 0. Does that make sense? So we're basically introducing a new unit of angle, and the size of that unit of angle is chosen so that there are exactly 2 to the 32 of those units in one rotation. There's 2 pi units of radians in one rotation. There's 360 degrees in one rotation. And there's 2 to the 32 units of accumulator in one rotation. Is that okay with people? So the consequence of this is rotating this phasor is the same as adding some amount to that variable. So if I have some amount of unit stored in accumulator and I add more to my accumulator variable, that's the same. It's interpreted as rotating this phasor a little bit more. And when we add all the way up to 2 to the 32 and it overflows, that's the same as this phasor approaching the positive real axis and then overflowing, going back to where it started. So that's the fundamental observation. So how is this actually used? I want to start by just introducing the steps of the algorithm, and then I want to justify some of those steps, because I think by doing it this way, well, I just think this is the right way to do it. I'm not sure of that, but I think this is the right way to do it. So you all know at this point that audio synthesis requires really precise timing. So in your lab 1, for example, we're using an audio synthesis rate of 44 kilohertz. What that means is at precisely 44 kilohertz, we send a new voltage to the DAC, which produces a sound. And the reason that we have to be precise is because your ears are sensitive to imprecision. If you have variation in your sample rate, you'll hear it. It's some sort of an artifact. So at exactly some rate, which we'll call F sub S, measured in hertz, at exactly some rate, we're sending new voltages to the DAC. And you achieve that timing with a timer interrupt. Now, as I mentioned, incrementing this accumulator variable is interpreted as rotating the phasor. So what that means is the faster you increment that variable, the faster this phasor is interpreted to be rotating. So you can see in this diagram here, we're incrementing this variable at some rate, which corresponds to a phasor rotation of some rate. If we increase the speed at which if we increase the increment to this accumulator variable, then this phasor rotates more quickly, and the consequence is we get a higher frequency sine wave out. So incrementing the phasor is incrementing the accumulator is interpreted as rotating the phasor. Okay, so why is that useful? This allows us to produce a sine wave of a very precise frequency by going through the following steps. And as I said, I'm going to talk through each of these steps sort of individually, but I want to introduce them first. And you've all seen this by now in the demo code. So in order to produce a sine wave of a desired frequency, you go through the following steps. You first enter an interrupt service routine. So you have some timer interrupt set up to enter an interrupt service routine at a very precise rate fs. We're using 44 kilohertz. When you get into the interrupt service routine, you add some amount to the accumulator, which, as we've talked about, is interpreted as rotating the phasor. So you enter the interrupt service routine, add some amount to the accumulator, which is the same as rotating that phasor a little bit to a slightly new angle. You look up the amplitude of the sine wave at that phasor angle. So in the example code, we have that sine table, right, which we use to go get sine amplitudes. So we enter the interrupt service routine. We rotate that phasor a little bit by adding a small amount to the accumulator variable. And then we go look up the amplitude of the sine wave at that angle. The angle I'm talking about is this angle here. So we enter the interrupt service routine. We rotate this phasor a little bit to a new angle, and we look up the amplitude of the sine wave at that angle. We then send that amplitude to the DAC. That's the voltage that we're going to output through the DAC. Leave the interrupt service routine, and we're done with that audio sample. And then 1 over fs later, 1 over 44,000 in the case of lab 1, seconds later, we re-enter the interrupt and do it all again. So you enter the interrupt, rotate the phasor, look up the sine amplitude and send it to the DAC, and leave the interrupt. And then you do it again. And the question is, you know, as we talked about, the more you add to that accumulator every time you enter the interrupt, the faster that phasor is rotating and the higher the frequency of the sine wave. So the obvious question is, for some desired output frequency, what's the correct amount to add to the accumulator every time you enter the interrupt? And that's what the direct digital synthesis algorithm tells you. It tells you precisely how much to add to that accumulator every time you interrupt to get an output frequency that you desire. We're going to talk through that in a moment. But does this make sense so far? So we've divided the 2 pi radians of phasor rotation into the 2 to the 32 units. We're using a 32-bit variable to represent that. The consequence of that is whenever that variable overflows, we've completed one period of the sine wave. And then the algorithm is very simply enter the interrupt service routine, add some amount to that accumulator, which is the same as rotating the phasor, look up the sine amplitude at that phasor angle, send it to the DAC, and leave. Wait 1 over fs seconds, and then do it all again. So let's think about this. Let's think about this increment. And there's an equation that tells you what this increment value should be, but I want to sort of justify where this equation comes from so we can think about this a little bit. And let's start by just considering what would be the output frequency that we would get if every time we entered the interrupt, we incremented our accumulator variable by 1 unit. So it's a 32-bit variable. What if every time we entered the interrupt service routine, we just added 1 to it, a 1 in the 0th bit? What would be our output frequency? Well, you can arrive at that output frequency just with basically dimensional analysis. So our output frequency here, which is measured in hertz, we can calculate this as by changing units. So this is a series of unit conversions. So we're going to start with units of overflows. So we have 1 sine period, which is to say 1 overflow of the variable every 2 to the 32 accumulator units. So every time, if you're starting with an accumulator value of 0, by the time you add 1, 2 to the 32 times, that variable will overflow, which, because we're using that to track phasor angle, that is the same as the phasor going around 1 time. So we have 1 sine period for every 2 to the 32 accumulator units. We're considering the case where we're adding exactly 1 every time we enter the audio interrupt service routine. So that means we have 1 accumulator unit every audio sample. And then we have some fixed audio rate. So we have FS audio samples per second. In our case in lab 1, we have 44,000 audio samples per second, which you set up with an interrupt service routine. So you can go through this and you end up with an output frequency of your audio sample rate over 2 to the 32, the maximum value that can be contained in your 32-bit accumulator variable. Which it turns out, if we look at this, so that's 44,000 divided by 2 to the 32. That's pretty low frequency. So we're looking at 1 to the minus 1, 2, 3, 4, 5 hertz. It's a pretty low frequency wave. In lab 1, we're producing sine waves of 2,000 to 7,000 hertz, right? But okay, so if you were to increment that accumulator variable by exactly 1 unit every time you enter the interrupt service routine, you would produce an output sine wave with this frequency. What if you were to increment it by 2 units every time you enter the interrupt service routine? Well, this looks basically the same, but as before, we have 1 sine period, one overflow of our accumulator variable every 2 to the 32 accumulator units. Now we're incrementing that accumulator by 2 units every audio sample. We have 2 accumulator units per audio sample. And as before, we have FS audio samples per second, 44,000 in the case of lab 1. So you end up with the same expression multiplied by 2 hertz. And at this point, you can recognize a pattern, right? So if we incremented the accumulator variable by some number n every time we entered the interrupt service routine, oh, that's a typo, that's a J, that should be n. But if we incremented this by some value n every time we enter the interrupt service routine, then it's the same expression where you just put n accumulator units per audio sample here, and your output frequency is your audio sample rate over 2 to the 32, the maximum number that you can contain in your accumulator variable, multiplied by n, your increment value. So you look at this and you can ask, well, what are the knowns and unknowns in this expression? And F out, the output frequency, is what you want. So you know F out because that's the frequency that you're trying to synthesize. Maybe it's 400 hertz, maybe it's 2000 hertz, whatever it is, you know what it is, whatever it is. FS, the audio sample rate, you know that too, because you set up the timer interrupt that sends audio samples to the DAC. So in the case of lab 1, you know this is 44 kilohertz because you made it 44 kilohertz. You know 2 to the 32 because you instantiated the accumulator variable as an int. So you know, or an unsigned int. So you know that you can hold 2 to the 32 units in the accumulator variable. So the only unknown in this expression is the increment value. So we can just rearrange this expression, and for some, what this will tell us is for some desired output frequency, we can solve for the increment amount in order to produce that output frequency. So suppose we want to produce 400 hertz, then our desired F out is 400 hertz. Our audio sample rate is, in our case, 44 kilohertz. And our accumulator variable is 32 bits long. So it holds 2 to the 32. So we can solve for the amount by which we need to increment our accumulator every audio interrupt in order to produce a 400 hertz output. We're going to look at some examples of this with actual numbers, and then we'll look at it in code. But for those of you that have been poking around in the demo code and working on lab 1, this is probably starting to look a little familiar to you. Right? This is one of the 2 lines that implements this algorithm. This is one of them. Okay. So let's just consider a simple example with numbers. So suppose you want to produce middle C, which is 262 hertz. And suppose that you're generating audio samples at 44 kilohertz using a timer interrupt. By how much should you increment the accumulator each time you produce a sample? So every time you enter that interrupt service routine, recall you're going to increment the accumulator, which is the same as rotating the phaser, look up the sine amplitude at that angle and send it to the DAC. How much should you add to that accumulator every time you enter the interrupt service routine to produce 262 hertz? Well, your desired F out is 262 hertz. Your audio sample rate is 44 kilohertz, 44,000. And your accumulator variable is 32 bits long. So it holds 2 to the 32. So you do this and you find out that, okay, every time we enter the interrupt service routine, we need to add this much to our accumulator variable. And if we do that, we'll produce 262 hertz. With how much precision, we're going to talk about in just a second. How close can you get to 262 hertz? Turns out shockingly close, but 260, that's how you do it. Questions about this? Okay. So let's talk a little bit about precision. So what is the resolution of our synthesizer using an accumulator variable with 32 bits in it? What we can arrive at this by, but this is essentially the same as asking, what is the frequency that is output when the accumulator is iterated by 1 unit every audio sample? It's how much frequency is contained in 1 unit of the accumulator. Is it clear that that's sort of the same question? The resolution is, you can produce a desired output frequency to within the amount of frequency that is contained within 1 unit of the accumulator variable, right? So the way to answer this question is to consider what's the output frequency that we get if we were to increment that accumulator by exactly 1 unit every time we enter the interrupt service routine, which we actually already talked about earlier. But if you do that, as we've already discovered, you end up with an output frequency of 1.02 times 10 to the minus 5th hertz. Which means with a 32-bit accumulator variable, you can hit a target frequency to within 1.02 times 10 to the minus 5th hertz. How might you start to get a sense for how could you measure that? You could use the oscilloscope. You could see how close that you're getting. Okay.
By the way, that's a frequency of 1 cycle per month.
That's an output sine wave with a frequency of 1 cycle per month. That's pretty slow, right? Okay, but a common question. So a very common question about this is, well, let me get to that in a second. But let's start by just considering, what if instead of using 32 bits to hold our phase accumulator, what if we used 16 bits? So instead of using an unsigned int, what if we used an unsigned short, which is 16 bits long? What would be the resolution of our synthesizer in that case? Well, in that case, it's basically the same expression, but instead of being able to hold values up to 2 to the 32, we can now hold values up to 2 to the 16. And you can see the resolution of our synthesizer is now 0.67 hertz. So by eliminating 16 variables from our accumulator variable, the resolution of our synthesizer goes from 1.02 times 10 to the minus 5th hertz down to 0.67 hertz. What if you only used 8 bits? What if you used a car to store your phase accumulator? In that case, very similar analysis shows that the resolution of your synthesizer is close to 172 hertz, just terrible, right? So you benefit from having extra bits in your phase accumulator variable. We'll talk more about that. Questions about this?
I have a question. Can we use floating points instead of fixed points because they have 32 bits as well?
So I don't recommend it for reasons that we're going to get into in a moment. We end up using that phase accumulator to index into a sine table. And if you're using a floating point representation, It's not obvious to me that you could do that without at least doing some sort of a typecast beforehand. Bruce, do you have comments about that?
Yes, I have a couple of comments. One is that floating point arithmetic is 50 times slower than fixed point, an integer. And you only have 900 cycles. And so every floating point multiply is 50 cycles off your budget. Every floating point add is 60 cycles off your budget. Every floating point divide is 150 cycles. So you dare not use floating point. If you can use fixed point, use fixed point. In this case, we're using integer because we can. Don't use more powerful arithmetic than you need, or you just waste CPU.
Those 900 cycles, that's if our audio sample rate is 44 kilohertz and we have a 40 megahertz CPU, that means there's about 900 CPU cycles between audio samples. So you have 900 cycles to spend on computing the next audio sample before that deadline approaches. So don't waste them on floating point is what Bruce was saying. Okay. So let's consider next this sine table. If you use a 32-bit unsigned int for your accumulator variables, then in principle, your accumulator variable can assume 2 to the 32 different states, right? But you don't need a sine lookup table that's 2 to the 32 elements long. In lab 1, we're using a sine lookup table that's 256 elements, 256 long. So the question is, how many is enough? What would be the consequence of having a longer sine lookup table? What would be the consequence of having a shorter sine lookup table? You can show that the less entries that you have in your sine table, the more harmonic distortion you're going to have in your generated tones. And the reason for this is that the DAC that we're using acts like a 0th order hold. So when you send a value to the DAC, it retains that value until you send the next value to the DAC. So the consequence of this is you end up, the output from the DAC will look like a squared off approximation of a sine wave. And how good this approximation is depends on how many elements you have in your sine lookup table. So you can see I'm going to play an animation here where in this particular example, we have 8 table entries in our sine lookup table, right? So if you count these, we have 8 steps in our sine here. And at the bottom, underneath of this, you can see the power spectrum associated with this curve. As I play this, you're going to notice a couple of things. The first thing that you're going to notice is the fundamental frequency for this curve is going to remain fixed at 1 cycle because we have 1 cycle of a sine wave represented here. But the error harmonics are going to move. And as you add more elements to the sine table, the first error harmonic moves away, increases in frequency, moves away from the fundamental, and the power of this first harmonic reduces. So, and in fact, the first harmonic will remain at approximately the number of entries in the table minus 1. So right now we have 8 entries in the table, so the first error fundamental is somewhere around 7 or so. And I'll point out too that this plot here is in log units. So 1 log unit corresponds to 20 dBs. So I'm just going to play this and you'll see what happens to notice what happens to the error harmonics as you increase the number of entries in your sine table. It's moving away and it's decreasing in amplitude. And this approximation to the curve is getting better and better. So the number of entries in your sine table depends in part on your requirements. What are your requirements for error harmonics? How pure does your tone need to be? For us, our requirement is really what sounds good. with 256 entries, to your ear, it will sound perfectly pure. And adding more entries to the sine table will add an amount of improvement that will be it's definitely impossible for me to discern. Maybe some of you have better ears for this sort of thing than I do. But the improvement that you get to your ear by adding more than 256 entries to your sine table is indiscernible. At 256 entries, the first error harmonic is so far away and so attenuated that it is imperceptible to my ear.
So if with 256 samples, as you've shown it here, the fundamental is at frequency 1 and the first error harmonic is above frequency 200. So if you're playing a frequency of middle C, 262 hertz, the first fundamental is at about 50 kilohertz, which you can't hear at all. Not even the best young ears can hear 50. Some of you can hear 22, 25. I can't hear 8, but never mind.
If you're curious about that too, by the way, there's online tone generators, and you can increase the frequency of the tone and see where you can't hear it anymore. It's kind of an interesting metric to actually track throughout your life if you care about these things, because it's going to change as you age. So if you want to, you could start now and every year see, oh, what's the highest frequency that I can hear, and see how it tracks as you age. Yeah, for me, it's somewhere up around 22 at the moment. Just when you do that, keep the volume low. As it becomes harder and harder to hear, you're tempted to increase the volume, which can be not good for your ears. So just keep the volume low as you do those sorts of tests on yourself. Any other questions or comments? I want to address some common questions about this. Okay, so let me first talk about this. So we have a 32-bit accumulator variable, and we have a sine table that's 256 elements long. So that means that with an 8-bit car, you could index into any index of that sine table, right? Because in 8 bits, you can hold values up to 256, right? So the question is, how do we use this phase accumulator in order to properly index into that 256 element sine table? The way to do this is to use, so this is the same animation as before. So you can see our phasor going around. This is the full value of our accumulator variable. Use the top 8 bits of this accumulator variable to index into that sine table. So a way to think about this is what this accumulator variable is telling you is it is keeping track of which index to enter into the sine table in a particular sample, where the top 8 bits of the accumulator variable are the integer part of that index, and the bottom 24 bits are the fractional part of the index. Now, clearly, you can't fractionally index into a sine table, right? It doesn't make any sense. So when you actually go to index into the sine table, you truncate out the whole bottom 24 bits and just index into whatever the top bits tell you to. This means that if you're synthesizing a lower frequency, right, these top 8 bits may not change for a few audio samples. You may index into precisely the same index of the sine table a few samples in a row, and that's okay. That's exactly what you want. But because this phase accumulator is keeping track of fractional indices, even though you aren't necessarily using that fractional index to actually enter you're truncating that out when you actually do the entering, because you're keeping track of fractional amounts of index, that means it will move to the next index at precisely the correct sample. So say, say you are adding, how do I want to talk about this? Say you're adding, a tenth of an index unit every time you interrupt into this interrupt service routine. That means that for 10 interrupts in a row, these top 8 integer parts of the index aren't going to change. The bottom parts, the fractional parts, will continue to increase, but you're going to index into the same the same index of your sine table 10 times in a row, but on the 11th, which is the correct one, you'll move to the next index of the sine table because you will have accumulated enough fractional amounts of index to pop up by 1. Does this make sense? So we have more bits in our phase accumulator than we require to index into our sine table. And we have that because we want to keep track of fractional amounts of index so that we can move to the next element of our sine table at the correct sample. We do that by accumulating fractional amounts of index until we move to the next integer value, and that's when we move to the next index of the sine table. So some common questions. The first one I kind of just answered, but a common question, one that I've gotten a few times in lab already is, if we only need 8 bits to index into the sine table, why does our phase accumulator need to be more than 8 bits? And it's for exactly the reason that I just said. This allows you to keep track of fractional amounts of index through your sine table, and to move to the next index of your sine table at the correct sample, at the correct time. And by the way, if we were in lab and if you could breadboard things, suppose that you wanted to improve these error harmonics, okay, without adding length to your sine table. Maybe there's some good reason that you don't want to do that. Another solution is to put a low pass filter between your DAC output and the speaker. And you decide where the cutoff frequency is, but you would put the cutoff frequency somewhere after, the fundamental and somewhere before the first harmonic. And you would attenuate this quite substantially, basically for free, right? For the cost of a little bit of extra hardware. Right? Use hardware when you can. It's helpful. Any questions about this? I thought next we could look at this in code. If that could be helpful. So let's do that. And interrupt me if something occurs to anyone. So let's look at the example code that you've been considering.
If I can inject one comment, it seems to bother people, in the past I've seen this, it seems to bother people that you may skip entries of the table or you may duplicate entries of the table. It's okay as long as you have more than about 8 or 16 samples per cycle. Keep the distortion down. You can skip it. You will skip some samples. You will duplicate some samples. That's how it works.
I'll add too that there's nothing in lab 1, we've somewhat arbitrarily decided on a sample rate of 44 kilohertz. There's nothing sacred about that number. It can be whatever you want for it to be. You just in the expressions here for calculating the increment amount, you just put whatever value you've decided on here. Now there's a practical upper limit, right? Because it takes a certain amount of cycles to actually get into an interrupt service routine and to get back out again. So there is some practical upper limit, but you could make this whatever you'd like and you can still get whatever your desired output frequency. You just have to accommodate whatever your chosen audio sample rate is in this expression for the increment amount. So let's look at this in code. And I want to start by going down to main, where you'll remember from the first couple of lectures, we looked at these 2 lines. This is where we are opening the timer that we're going to use to actually be sending audio samples to the DAC. And we're having this timer time out, that is to say overflow and interrupt, every 40 million over FS cycles, FS being our audio sample rate. So that's defined up above. FS is In the example code, it's set to 40 kilohertz. Like I said, that's fine. It just needs to be accommodated for in the direct digital synthesis algorithm. So we're interrupting every 40 million over fs cycles. If that were 44 kilohertz, that would end up being about 909, like we already talked about. So at exactly that rate, we're going to enter the audio synthesis interrupt service routine, which is here. This is the interrupt service routine tied to the timer 2 vector. So this is the one that we enter every time that timer overflows. And the whole algorithm is contained right here. So we have this phase accumulator. This is that 32-bit value that we're using to keep track of the accumulator variable, which we're interpreting as the angle of that phasor. So the two steps are, we increment that phase accumulator by some amount, in this code we're calling phase increment main. We increment it, move that phasor to a new angle, and then we look up the amplitude of the sine wave at that angle. I've gotten some questions about this shift right by 24. This is because we're using the top 8 bits of the phase accumulator variable to index into the sine table. So we just shift right, we truncate out all the fractional part. And we're just indexing into this 256 element sine table using the top 8 bits of phase accumulator. So we increment our accumulator, we look up the sine amplitude at that accumulator value, and we write it to the DAC. And that's all that happens. So the degree of freedom here, once you've set this up, the degree of freedom that you manipulate in order to produce different frequencies is this phase increment. In the example code, this phase increment is manipulated in the slider thread, because you'll remember in the example code, you can slide that slider, right, and produce different frequencies. So if we take a look at the slider thread, you can see here that we are setting the value of that increment to the slider value, which is the desired output frequency, times 2 to the 32 over the audio sample frequency. This is this. So for some desired output frequency, F out, which is the slider value, that's F out, we compute our phase increment, N in this example, by F out over Fs times 2 to the 32. F out over Fs times 2 to the 32, or F out times 2 to the 32 over Fs, same thing, right? So in this thread, we compute our phase increment. With that phase increment that corresponds to a particular desired output frequency, in our interrupt service routine, we then very simply add that amount to our accumulator, and then use the top 8 bits of that accumulator to index into the sine table. Grab that amplitude from the sine table, send it to the DAC, leave the interrupt service routine, and 1 over Fs seconds later, re-enter and do it again. So what's that sound and look like? This is exactly the same demo code. If I run this, right, this is the user interface that you've all been messing with. This is where we're setting our desired output frequency. If I unmute this, this is now going to be at 400 hertz. As I slide that, what I'm changing is F out in that expression, in the slider thread. What I'm changing as I slide that is this slider value, so desired frequency. How might you tell how good you're doing? Well, you can open up the attached oscilloscope, right, which is attached to the DAC output here. I have a measurement open that's showing us our output frequency. Right now it's at 382-ish hertz. If we look at 381, 382, it's exactly what we're specifying, to within the accuracy that we expect. As I move this, okay, you can see our output frequency is tracking our desired frequency. Okay. So use the scope. Use the scope to make sure that you're getting the expected output from your DAC. That the output from your DAC agrees with what you would expect given your understanding of how direct digital synthesis works. Very briefly, I'll just mention here at the end. In lab 1, let me show code here in just a second. What's different about lab 1 is we aren't producing constant tones. So what that means is, so this is the spectrogram we're considering in lab 1, right? This is showing you as a function of time what your desired output frequency is. And you can see that it changes with time. So there's two, like we've talked about a few times, there's two sound primitives going on in the song. There's a swoop and then a chirp, right? So each lasts 130 milliseconds. In that expression up above, sorry, I'm doing a lot of scrolling, but I just want to point something out. In this expression up above, what that means is F out here is a function of time. So in that interrupt service routine, you need to be keeping track of how many interrupts into this sound am I? So you're incrementing some value every time you enter the interrupt to keep track of how long have I been producing that sound? And then you need to compute the desired output frequency at that time. So the desired output frequency is a function of time. We do that by fitting those frequency curves to functions of time. And the unit of time that makes the most sense in lab is audio samples, right? So we compute frequency as a function of number of audio samples. And if we consider, for example, the chirp part of this, right? The chirp, the high to low, or low to high rather, that looks kind of like a quadratic function. So we can fit that curve to a quadratic of the form y equals kx squared plus b, right? Where y is the desired output frequency and x is the number of audio samples that have occurred since that sound began, which you're incrementing in your interrupt service routine. You can fit, you can look at the spectrogram and say, okay, we're starting at about 2 kilohertz, ending at about 7 kilohertz, and get your expression. And then for a certain number of samples into a sound, you can compute the desired output frequency, for which you then turn the crank on the direct digital synthesis algorithm. Now, I want to point out a couple things that you can get away with in this lab and a couple of things you can't get away with in this lab. You can't get away with pre-computing all of these frequencies and storing them in a large array. You're not going to have enough memory to do that. You have to compute these on the fly. So every audio sample, you have to look at, okay, how far into this sound am I? What's the output frequency that I desire at that amount of time into the sound? Compute it and then run direct digital synthesis. You can't store these but pre-computed. Okay, so then the next question is, do I have time to do this in floating point? It turns out in this case you do, but barely, but barely. So you can get away with doing this calculation in floating point for this lab. As Bruce said, you have about 900 cycles to spend, which is not that many. It is just enough to do this in floating point. In the next lab, you're not going to be able to get away with that. In the next lab, it's got to be fixed point arithmetic. And we're going to talk about that quite a bit. In this lab, with 900 cycles at a 44 kilohertz sample rate, you can get away with doing this computation in floating point. If you wanted to do this in the most optimal way, which is to say, in the way that spends the least amount of CPU cycles, you would do this you would figure out a way to do this calculation using integer arithmetic. And you may even start to do clever things like, this is a suggestion by that Bruce made in one of the labs, is you might, instead of considering the function itself, you might start thinking about the derivative of that function, and instead of using the function to compute the desired output frequency as a function of the number of samples, you would instead Euler integrate its derivative. If you integrate the derivative of a function, you get the function back out, right? So you get the same values, but the math associated with computing derivatives here is more efficient. It ends up being multiplies and adds. And in fact, it's even multiplies by 2. So that's shifts and adds as opposed to squaring values, which is faster. But like I said, not strictly required for lab 1. You can meet the lab 1 timing deadlines with floating point. Won't be the case for lab 2, but it is the case for lab 1. And just because it's fun. That's what those sweeps sound like, right? Which some of you have started generating in lab. Okay, we're out of time, I suppose. Are there any questions? Read over that web page on your own time also. Experience shows that with this algorithm, it can take a little bit of kind of staring at the ceiling and thinking about it. But it's a really powerful algorithm to get comfortable with because it does not cost much CPU at all to produce a huge amount of various frequencies with unbelievable precision. So its efficiency is astounding, and what you get for that efficiency with this algorithm is also astounding. So it's a good one to have in your toolkit, just like moving forward. It's a good one to understand. So take some time to read through the web page on your own time, and then if you want to ask questions about it in lab or in a subsequent lecture, I'd be happy to talk more about this.